Precision analog-to-digital converters are the critical enabling interface between real-world signals and the power of modern digital processing in applications ranging from industrial process control to high-end test and measurement systems. Unfortunately, it's not always easy to connect sensors or other signal sources to a converter and get all the performance the data converter advertises. Additional circuitry is often needed which provides buffering, voltage protection, or other functions, which can be challenging to implement with the required performance. Hi, I'm Andrew Thomas, a senior design engineer in the mixed signal group at Linear Technology, and I'd like to show you how the integrated picoamp input analog buffers of our new LTC2358 octal ADC can simplify these challenges. In essence, we've taken the leading performance and outstanding flexibility of our LTC2348 octal successive approximation ADC and added high-performance fed input buffering. In the LTC2348 product video, we discussed how its outstanding performance and arbitrary input measurement capability make it an excellent choice for many high-voltage applications. The LTC2358 shares these advantages with nearly identical performance. Now, though, I'd like to focus on some simple ways its buffered inputs can improve your system. Many sensors, even those with outputs that are slow or delicate, can simply be connected directly to the LTC2358 without any intermediate signal conditioning. Where previously an octal ADC might have required buffering from 4 dual high-voltage op-amps like this, the LTC2358 offers a dramatic savings in board area and power by eliminating those op-amps. One example of such a direct sensor connection is the simple thermistor circuit shown here, which produces a voltage at the ADC related to the ratio of the thermistor to the fixed resistor above. Notice that connecting the top of the resistor to the ADC reference ensures an accurate ratio even if the reference drifts. When selecting a thermistor, low resistance values result in greater power dissipation in the thermistor, which can compromise measurement accuracy. On the other hand, accuracy with a high resistance thermistor requires very high input impedance measurement. Here, the purely capacitive input of the LTC2358 shines, allowing good accuracy with a 20 kilo ohm element. The LTC2358's high sample rate and low noise allow a further improvement of using a switch in parallel with the thermistor. While this switch is on, no power is dissipated in the thermistor, so it will be at ambient temperature. When a temperature measurement is needed, the switch is briefly turned off, and the measurement can then be completed in under a millisecond, before the thermistor has time to heat itself. This plot shows how quickly an accurate measurement can be taken, and also the increasing measurement error if conversion is continued for 100 milliseconds, well beyond the time required. That simple example shows how easy it can be to interface between a sensor and the LTC2358. But the buffers help in other ways as well. Changing focus a bit, the buffered inputs also make it easy to design a system to handle overrange signals cleanly and transparently, whether they arise as part of normal behavior or a system fault condition. Overrange ADC input signals can occur for a number of reasons. Sometimes they're as obvious as putting a 2 kilogram object on a 1 kilogram scale. Or they can result from malfunctioning sensors, power supplies, and wiring. Accounting for these conditions is at best a distraction, and at worst compromises performance. The LTC2358 helps make it easier to build high-performance systems that are robust to overrange signals. This colored bar shows graphically how the LTC2358 can be expected to behave with various input voltages. Firstly, the ADC has no difficulties when analog input voltages exceed their programmed full scale. For instance, if an input is configured for 0 to 5 volt operation, but the system applies 10 volts or any voltage up to the high voltage supply difference, the converter simply reports a saturated full scale value. Results converted on other channels are still accurate, and power dissipation does not increase. In more severe cases, the inputs might be driven beyond the high voltage supplies. For example, if an amplifier supplied from 40 volts drives the ADC, that amplifier might try to drive an input to 40 volts in an abnormal condition. Internal diodes clamp the analog inputs to the high voltage supplies, so it is simply necessary to limit the current to avoid damaging the part or other circuitry. The LTC2358 can tolerate pins pulled beyond its supplies with up to 10 milliamps without concern. So simply placing a 2.5 kilo-ohm resistor in series with the input can allow for a spurious input signal going to 40 volts. The high impedance inputs of the ADC ensure that this series resistance does not degrade performance when the circuit is operating normally, and voltages up to 40 volts cause no accuracy effect on other ADC channels. Pulling inputs below the negative supply down to minus 40 volts will also not cause damage, but will corrupt the accuracy on other channels. Beyond these limits, power dissipation in the ADC and resistors risks damage. Other values of resistor can be used for other possible ranges of overdrive, keeping in mind the 10 milliamp current limit. For example, a 10 kilo-ohm resistor would allow 100 volts. Notice that the power dissipation with 100 volts across 10 kilo-ohms is 1 watt, so a higher power resistor is required. But the solution is still extremely simple and robust. So far, I've shown a couple examples of how the circuitry in front of the ADC can be eliminated or simplified. The LTC2358 can also be integrated into sensing systems in some more inventive ways, which leverage its extremely low input current and wide common mode range. The analog input current is solely determined by junction leakage and is typically less than 10 picoamps at room temperature. This low input current means that the LTC2358 can be used with extremely low-level current signals, as are typical of photodiodes. A photodiode is a reverse bias diode designed to conduct a small amount of current determined by the light level shining on the diode. This small current signal is then often converted to a voltage by a transimpedance op-amp circuit like this one, so that the output voltage of the op-amp is proportional to the diode current and may be digitized by an ADC. Since the photodiode is a reverse diode, it looks like an extremely high resistance, and measuring its current with high accuracy requires that anything connected to it have extremely low input current. Thus, the op-amp shown must usually be a FET input op-amp. Unfortunately, the input offset voltage of FET op-amps is typically not very good, which affects the accuracy of the output voltage. However, the LTC2358 is capable of making differential measurements, so it may be connected to measure the voltage across the resistor instead of at the output of the op-amp. This connection cancels out the effect of the op-amp offset and low-frequency noise in the measurement. It's important to note here that this circuit only works because the LTC2358 itself has a very low input current, typically only a few picoamps at room temperature, so it may reasonably be connected directly to the photodiode without disturbing the measurement. This photodiode circuit is just one example of a broad class of applications and circuits made possible by the buffered inputs of the LTC2358. To name a few more cases, it's also considerably easier to design analog signal filters and interface with low-power op-amps. Adding this capability to the simple overdrive robustness, direct sensor connection, and outstanding raw performance makes the LTC2358 a remarkable solution for a great number of multi-channel systems. Hopefully, I've shown you some ways it can make your next system design easier. For more information, please visit us at linear.com. Thanks for watching.